All right. So we were talking about there must be an easier way than listing this for all the electrons in an atom. So we talked about the fact that when they have the same N, they're in the electrons are in the same shell. When they have the same N and the same L, then they're in the same subshell inside that shell. They thought that they would name the N equals 1 shell K, N equals 2 shell L, and M equals 3 shell M, etc. Now they thought that. In the end, they didn't go this route. And when we get to nuclear, we'll talk about this K shell, the N equals 1 being the K shell. In one instance, it's about the only spot that I've ever seen it referred to as the K. So then they decided to name the subshells, S, P, D, F, G. So S stands for sharp, P for principal, D for diffuse, F for fundamental, and then G onward is going to be in alphabetical order. Okay? Now, what Pauli's exclusion principle tells us that in any given L, in any given for any given subshell, there can be 2L plus 1 different values for ML, right? So if L equals 0, then ML has to equal just 0 and there's only one value. If L equals 1, then 2 times 1 is 2 plus 1 is 3, and we know ML can be -1, 0, or 1. If L equals 2, then ML can have 5 values because it would be 2, -2, -1, 0, 1, and 2. Okay? So this tells us how many MLs there would be. And so we can get the number of electrons, since Pauli's exclusion principle tells us there can be 2 electrons in each ML, then the number of electrons for any given subshell will be 2 brackets 2L plus 1. That will tell us the number of electrons allowed in our SP, D, Fs, etc. Right? So in our S shell, L equals 0. So this will be 2. Right? 2 times 0 plus 1 is 1 times 2. In our P shell, that's L equals, so this was L equals 0. And when L equals 1, 1 times 2 is 2, plus 1 is 3 times 2, there can be 6. For our D shell, L equals 2. 2 times 2 is 4, plus 1 is 5, times 2 is 10. And for our F shell, L is equal to 3. 3 times 2 is 6, plus 1 is 7, times 2 is 14. And our G shell would be L equals 4 subshell. 4 times 2 is 8, plus 1 is 9, times 2 would be 18. Okay? And then they would keep going up. All right? So this will tell us how many electrons can be in each subshell. So then what they decided to do was write the number for the N, because it didn't make any sense to have 2 sets of letters. So the number for the N, the letter for the L, and then the superscript would be the number of electrons. So calcium then would become, so when N equals 1, L equals 0, so it would be 1s, and there's 2 of them, 1s2. And then we go to N equals 2, and the first one is S, and there's 2 of them, so 2s2. Then still in 2, we're now in L equals 1, which is P, so 2P, 1, 2, 3, 4, 5, 6. Next up, 3s, and there's 2 of them. And then, so that was another subshell. Here's the next 6, except I think I missed one. Okay, and so it would be 3p6. And so it looks like they're going to fill in order here. But actually what we've discovered is that there's a few, they don't completely fill in order, because the 4s is actually a lower energy than the 3d. Remember the, I don't know, was it yesterday or today? Might have been today. I don't know. It was some day in class. I was doing the mLs, right? So I was saying, okay, this is n equals 1. This is n equals 2. But for n equals 2, there are two levels. There's the L equals 0 and the L equals 1. And then within that, there's subdivisions where ML equals -1, 0, and 1. And then n equals 3, it splits as well, right? And so we might think it splits like this, but what we've actually realized, so this is L equals 0, L equals 1, L equals 2, and then when we get to the n equals 4, it is going to split as well. And what we've discovered is that the S ends up lower than the one of the lines in the 3. Okay? And so 4S is actually going to fill before 3D. And so over down here, when I put an asterisk here, it's because I know that 3 doesn't fill next. 4s is actually lower, has a lower energy than 3d. And so what will happen here is that these ones will go to 4. And when 4 can be 0, 1, 2, 3, it'll go to 0. It will go to 0, 1/2, 4, 0, 0, -1/2. And so to complete the shortcut way of doing it, this will be 4s2. And this is called the electron configuration. This is 2, but it's way messier. Now this exception we can always find using something that's called Offpass diagram. And some of you may have seen it in grade 11. It probably just depends on which semester you had it. Okay, so Offpass diagram, you write 1s, 2, oops, that's supposed to be a 2. It looks an awful lot like a 1. 3s, 4s, 5s, 6s, 7s, may as well do 8s just for fun. And then 2p, 3p, 4p, 5p, 6p, 7p, 8p, 3d, because they can't have, 1 can't have a p and 2 can't have a d, 4d, 5d, 6d, 7d. I'm just stopping there because I know I don't need it right now. Whoops, that would be good if that was a 4 and not a 5. 4f, 5f, 6f, 7f, okay, fine, 8d, 8f, and then on this one would be 5g, 6g, 7g, 8g, etc. So you do this thing out, and so you might think it'll go it'll fill in order, but it really doesn't. Instead, the way you fill it is you draw diagonal arrows, and so it fills following the arrows, right? So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f5, okay? So you don't need to memorize it. You just draw this little configuration when you go to do the electron configurations, and you can always figure it out. So it's called Offpass diagram. Offpass diagram. Okay? And so it shows the energy levels that should fill in order. And that was how I knew that after 3p was going to come 4s before 3d. And it's because the 4s orbital has lower energy than the 3d orbital, and it will always fill lowest energy first. Okay?